So then now, called this section Learning to Plan because it's sort of, everything is still true, but we talked about in the last slides, but now we will add in, okay, now you have to learn your model and it'll never be perfect. So it's kind of this, sorry, chunk here. Just open up the actual slides. Great. It's basically now, all right. Now there's no system or something that is given to the actual agent that does understand the dynamics. So there's no more perfect world model dynamics model the agent has. It does have the option to at least be able to learn it, but then how do we go about this learning process? So we'll talk about more. So it's still the same objective. Just agent starts out with less information about how the world works. Still the same reward along the trajectory. So that part hasn't changed. Great. So the concepts here, and again, there's a bit of a terminology introduction in this, often this is called model-based reinforcement learning. If it's from the reinforcement learning community, it's from the robotics and kind of trajectory optimization community. It's called model predictive control, which is just basically the agent has some model, whether or not it's accurate. So you could say this is learning the model, but still doing model predictive control. Just in case you're going through some of the details for this. But the real question is, okay, why would we want to learn a model? I think part of that should be pretty obvious. I mean, for most problems, well, okay, the dynamics are unknown, even though, in the school, there are physics departments and chemistry departments. They've got pretty good models for how the world works. But in this case, the agent, we basically want to make a learning agent that doesn't have as many assumptions, and it can figure this stuff out on its own. If we're as researchers and as a community lucky enough, we kind of carry this design paradigm into the future. Eventually, it helps us figure out dynamics for stuff we don't even know yet. So maybe there's some priors that can be included, but there's also a ton of open questions about how the dynamics of the universe works. Hopefully, some of these will be able to help us answer a few of those questions in the future. We'll see. So then the challenge is basically learning the forward dynamics model. It's easy, right? If I asked everyone in this room right now to write down the forward dynamics model for the universe, you could do that. No problem. Even though you've already had 20 plus years of practice so far. Probably not. Okay. But then we can have this basic model-based RL algorithm, collect a bunch of experience in some environment using some policy. This could be random. This could kind of be anything right now, but we'll get to some of the details about that. Basically here, just do a little bit of mean squared error to be able to reduce and predict for your model better for the agent, and then use this model, plan high value trajectories. Sounds great, right? Any issues that you think might happen already with this algorithm? So I'll get to this a bit more in the next slide. One way to be able to think about this is also a version of doing system identification again, collect data, figure out how the dynamics works. In robotics, this is usually used to figure out joint friction, something like that, not how the entire world and how it unfolds, but it still could be classified under the group of stuff for system identification, depending on how much we stretch that definition. But there's still a number of challenges. This definitely can work well, being able to learn this model, especially when there's some engineered representations. And this is really where a lot of that background from model predictive control comes from. That model is usually given to the algorithm from some people who did a lot of work figuring out how the dynamics for that robot is going to work. Figuring out the friction, weighing the robot down to sometimes the milligram, figuring out how it will react, understanding the torques and the controls for the robot and how fast those actually happen. So a lot of effort can go into that and learning that process and be able to design this representation. You get really good results. When that's done well enough, you basically end up more like the last set of slides, which is the algorithm is given this really good model. And it also works really well when there's a really good physics prior or where there's some really low dimensional state. And this is these days an example of a really low dimensional state. So it's just like the rotations of the joints and maybe how like the velocity of all those links and how they're currently going through the universe. All right. So, but how well does model-based RL really work? Think about this process. So now we can discuss this. Why is at least, this version of the algorithm here not going to work very well? Any ideas? Yeah. hmm Yeah, exactly. The environment can change in any way too. I don't know if all of you just noticed the ice falling off the roof too. So the environment is changing without us even like permitting it to change. So it's going to. But this happens a lot. And this is basically an example of what can happen here. But the environment changes, that's like the cause. The effect of this is that the agent, and I kind of can draw something like this. Maybe that's like threads on some particular robot. And we said here in the beginning that this is going to collect data from some policy. So now this robot might travel around here, do kind of well, be able to collect some of that data. And the reward function for this agent could be, travel to the highest peak that's currently on this cliff. So it's going to go this way. And then what is it going to be told to do at this point when it gets to the highest peak? It doesn't have any data there. It's going to be basically told, keep going to the right. Nothing in the data right now says that it should not go to the right at any point in what it's been trained on so far. So our unfortunate robot for now is going to end up at the bottom of this cliff. Maybe the next robot will do better, but not if it's using the exact same data or algorithm. But yeah, this is basically something about this is changing. I think like if the environment is changing, it's a harder version of this. This is also, even if the environment doesn't change, but it doesn't have data in some part of the environment, then it's also basically the same problem. But this can happen before it even gets to like snow falling off the roof, things like that. Okay, so this really, both ways of thinking about this is that, okay, this is really a question of support inside of the data set that's being used to train the model. And this is basically a definition. There should be some probability in the data set that the state the agent is going to visit. It's like that probability for that state is like non-zero in the data set. So there's some amount of support under the definition for this. And then depending on how much support there is, you kind of get a different answer. But if there is no support, then most likely like the policy or the forward model there is not going to give good predictions. Sometimes you get lucky, or you can follow some of these steps for making a really well engineered representation. But often these engineered representations are also saying, okay, in all of these states that there isn't currently data, the model still assumes the dynamics unfold this way. It's a bit of a cheat, but it's usually reasonable enough. Okay. Yes.
Or is this definition, is it conditional on the policy?
Hmm.
Or you have a proper policy that probability of this every state?
So this, at least definition on the page here, isn't that detailed because, we can pick the lazy case with to say like, well, we want support over the entire state space. Then at least we'll know we'll have some data in all possible places. And then that's at least some amount of support. But yeah, a slightly better version of this support is that, well, we really want support in terms of the higher value states that the agent is going to end up visiting. But, the best way to be able to get that is to essentially now take the agent, the robot, okay, have it rerun, collect some data in this area, rerun it again, it gets over here, collect some new data. So like really this random policy is kind of the problem in the beginning. It just collects some data. It's not covering the state space. It's also not covering the area that policy is going to be instructed to go. So it's both of these problems. So then from that, that's basically part of the solution. is we need to figure out, instead of totally having this random policy that's collecting the data to provide the support for this forward dynamics model, then we need to figure out, all right, how can we make these two equal? Any ideas? And by these two, it's sort of like the distribution of data that's being collected is going to be for the support for where the policy is going to go. Any thoughts? Nothing about this kind of question in any of the papers that you read for this week? They usually skip over these details and just assume, oh, more data, bigger model solves everything, which is basically what I'm saying right now is like, no, it doesn't. And not unless you do it really carefully. Ideas? Iterate on what? Yeah, okay. Newer data with that policy. Well, the word that here will probably still add a bit more to the details, but the answer is almost always this: need more what's called on policy data. And on policy means like whatever policy is going to be used to control the agent in the environment, we need data from that thing, not some random policy, and not even some slightly back in history time policy. It needs to be absolutely the current policy. It's the only way to make sure that the data is collected is in the support that's needed for the current policy. So this at least doesn't require too much of a change to the current algorithm, but basically now instead of just having like the 3 steps, now we've got a different loop. So it can still collect some data to do some pre-training, but now basically use that model, plan a plan in there, execute some of that plan inside of the environment, use that data, retrain the forward dynamics model from that data. And now it'll always be able to get support in the area it ends up traveling inside of the state space. And eventually it'll do better. I mean, it's true, it'll get like some support. It'll definitely go into areas it doesn't know, but it will be able to update its model. At least, you know, if we're lucky enough to do all this in simulation and we don't do it in the real world and basically burn our way through many, many robots that fall into this cliff. And this is one reason why, you know, using simulation can be helpful. Okay, does that make sense? All right, this is always like a really important concept that there's like, yeah, option 1 for support, cover the entire universe and all possible data you could ever need. You're welcome to pursue that one or anyone else wants, but on policy data will always be likely more helpful, more aligned, and you won't need as much. And I'll get to it a bit in the end, but like talking about this and talking about amounts of data is what's really on a lot of people's minds lately, at least in terms of robotics. Because, you know, it costs money to collect data. So now we kind of want these versions that are going to work well and collect the smallest amount of data to be able to work well, not cover the entire universe and collect all the data as possible. Okay. Questions? So, yeah, definitely some algorithms and more that we'll talk about will use more off-policy data. Yes, we'll call it cost for now. Usually the term you'll see in a paper is like sample efficiency, but let's just say like every sample costs some amount of dollars, so you want to keep that cost down. Cost is usually time as well, or as another way to think about it. But those are the things that are on people's minds. And it's true that there's some other ways to kind of bend this algorithm a bit more. So you could collect data across more robots, and then you can maybe parallelize the cost. So you reduce time, you don't reduce money in that case, because, well, maybe by some factor, maybe it's kind of sublinear. I'm not sure about that just yet, but you would increase time for being able to collect enough data. These are all somewhat equivalent. How do we choose it? I mean, I would like to be able to say that some algorithms are better at being able to choose this experience, but because now this is basically just coming from this policy. So it's going to choose this based on whatever is going to seemingly give the agent a high value plan according to its current model. That's what'll happen for this algorithm, but that's not really what we want to do in all cases. There's some versions of using things like trying to cover the state space. So maybe the one way to do this is to like maybe this state or stuff that hasn't been seen before. And we'll talk about a few of those a bit later in the class, or maybe half of what the agent should collect is from this exact algorithm, and half of it should actually be where that forward dynamics model doesn't predict well, because then it should learn about things that it doesn't know, just in case it's missing something, which is like heavily in line with things like upper confidence bound exploration. Like try stuff that seemingly looks good now and some random stuff, and the combination of those two allow the agent to like theoretically converge to an optimal solution. But some balance between these. And this is a little bit where the art will come in terms of like doing RL and robotics. Because yeah, picking what to helping the agent or providing some distribution it should use to help select what actions and states. It's really a tricky thing to do. And it's I don't know, people are really good at this thing. Robots are quite terrible at this type of thing. Most algorithms, at least, are pretty inefficient. Okay. Other questions? All right. So there's still definitely some of these problems with planning. One thing here is this was plan a high value trajectory, which means that this is going to compute basically an entire plan, and then the agent is going to follow that plan unquestionably, which I don't think is something many of you have done. Like even if you probably computed a plan for today, yeah, how many of you knew how to get to this room? You kind of just went on trust because of me for some reason. Hopefully I'll keep that trust for a little while. But you know, if the problem ends up being too open loop, all right, how long into the future should this plan be constructed for the agent? This is kind of related to a bit of our discussion on like when does it need to make a decision according to like how things are changing in the world. So if a car is driving, you know, this could start to deviate a little bit over time. At some point, because it's trying to follow this plan, but there's some error in its forward dynamics model and how it used its plan. So then at some point, this agent needs to now replan. It's getting pretty far off track from this center line on the road. And then hopefully this new plan will at least try to get it back on track. And then the new plan will probably go too far, and then it'll need to replan again. So basically, we think about this process when this plan increases, it's kind of like putting trust in this forward dynamics model more and more. As the length of this plan increases, a lot more error can creep in. And that's not just because of the forward dynamics model, but it's just sort of like, as we've talked about before, very much like how it's done for Dagger, you know, error is going to accumulate, and it's also going to be pretty bad over time. Can increase quite quickly, depending on the model. So then there's always going to be a hyperparameter, which isn't really talked about much in papers. It's probably going to be like one of the first partly annoying things you have to deal with in the like programming assignment for the class. Is how far into the future should the agent plan? Like if you've ever done RL before, there's usually like a hyperparameter for how long is the trajectory that the agent collects. And it's basically the same process. And that number is incredibly important to like show off when you compare algorithms even. So I mostly want to focus here on the agent should be planning for some distance into the future. That might be good to consider how long that plan should be. But there's also a second part where like evaluating different algorithms, if this planning length changes, might get different answers for different reasons. And this is where we'll cover a lot of the stuff in the rest of this lecture. Everyone's awake, right? Good. So now we'll start talking about more of like the practical forward models that people are using these days and why, you know, for different types of agents, you might choose different forward dynamics models depending on how long that thing is going to plan into the future for the type of problem that you've got. Okay, does that make sense? Great. Okay, so this is where the goal is to be able to like close this loop on planning a little bit more. There's obviously the one way to be able to start this is basically, the agent really only makes one action. So maybe the algorithm currently computes a plan for the next 5 years, but what actually ends up happening is in practice, the agent will only take the first action from that plan, apply it in the real world, and replan, throwing out the next 4 years and I don't know, 99% of the fifth year. And this does make it at least good and closed loop, so it'll react. It may waste a whole lot of compute, but if the agent doesn't plan far enough into the future, then it actually is going to be suboptimal in being able to reach its goal. It has to plan some amount of distance. Otherwise, it ends up being extremely greedy when it's trying to compute like that trajectory cost for some long time into the future. Or if you're doing stuff in RL and you have that discount factor, which is kind of equivalent to T, if the planning trajectory is really short, it's not going to take into consideration certain things. So for example, I don't know, if you want to figure out what to do for dinner tonight, you at least need to plan that far ahead and start to think about where to go. But if you're only worrying about the next 2 minutes and the agent has no concept of hunger, it's not going to start to have any forethought about what to do about finding food in the future. Okay. So this is where, the next step in this, but also kind of one of the simpler versions of this, is to basically execute just the first action from this plan. So there's a whole lot of planning being going on, really a whole lot of wasted computation, somewhat to be able to compute a lot for stuff into the future. And then the agent just takes one action, executes that in the world, and then goes back to do the next step, replanning all over again. And remember, this replanning step can potentially be exponential in terms of how many, explorations or samples from that 4 dynamics model it needs to do in order to at least come up with a plan that seemingly looks optimal from that state. Okay, does that make sense? This is kind of, sure, we've got really grand ideas about planning 10 years into the future, but really we're taking like a few actions at a time, and then we'll see whether or not those actions align with the plan and the outcome that we hoped was going to happen. And the agent can do something like this. And there certainly is there's a lot of papers that now kind of blend these ideas, whether or not it's like event-based planning. So follow the plan until some event happens, then it has to replan. So then at least it replan every single step. And then there's the other avenue of this where algorithms will try to reuse as much of this plan as possible. So if the agent is still being able to move around in the world, the plan seems like it's going well, then maybe it can reuse a lot of the computation, even though it's replanning each time. So at least, the agent can keep some sort of distribution over this plan. Maybe not quite something like the chem method we were talking about, but something about that distribution at plan should be useful some way. Okay. So there's still definitely some challenges. Even with using this algorithm, it can work. It can work well. I'll talk a little bit more at the end of these slides about some of the other challenges. Basically, replanning almost always helps because there's always going to be some error in the forward prediction model, so that dynamics model. So there'll be the agent, after it takes the action in that plan, is not going to be exactly in the state it thought it was going to be in. So then the more often the agent plans, the higher value it'll actually stay on track for a plan. Often, actually, this might be weird, but using shorter horizons can help. This is a bit more of an in-practice thing. So if the agent has X amount of compute and it's going to use that in some way, it's either going to plan longer trajectories, and that means if it's doing that, it's actually going to do fewer trajectories it's going to roll out, or if it does shorter trajectories, it has more compute to roll out more trajectories and maybe find a higher value plan. So if your agent is compute limited, there's definitely some hyperparameters here to kind of play around with in order to get better performance. Often depends on just the difficulty of the task that the agent is facing. All right. And then, you can start out, the agent can start out nice and simple in terms of planning algorithms. And then there are many papers, as I was saying, that figures out much better ways to do this planning here. There's like a whole community in robotics is trying to do this well. Okay. Any questions? One. Ah, perfect. Yeah, great. Let's take a break there. It's already 1:50. I know it seems like it was fast. Yeah, and there's, I guess we've already been here once before, but yeah, like the bathrooms are down the hall. And there's now and also still like a cafe right across the hall too, if you want to go get something to drink, etc. Hey, how you doing? Pretty good. Yeah, as long as you're not the cause of the ice melting. Okay, yeah. Don't worry about it. Thank you.
Didn't I sent an email about the Discord link that is expired? Would
Right.
it be too hard to generate one invite right now?
No, I'll do that right now.
Thanks.
I noticed the class hour late. I came here thinking it was 2, but sorry.
Oh, okay, it's okay. I mean, I'll make the recordings too, so I can share what we've talked about already.
That's good to know.
You can catch up already.
Yes. And sorry, I wasn't able to come to the first class last week
Mhm.
because I had a family situation. I need to go back to my home country. So I'm here like I came here yesterday or 2 days ago, I think.
Okay.
So this will be my first.
Are you enrolled in the course already? And like, are
Yes,
you
I-
on the Discord?
I'm enrolled, but I'm not in the Discord.
Okay, so send me a message for that, because I'll share the recordings for the class so you can catch up and watch
Okay,
those.
I can send an email.
Yeah, that would be
Or you
good.
can just get the Discord link now.
Yeah, well, I've got
That
to
can-
email both of you, or is it easy enough to do that?
Actually, I'm not sure if you received my email because I sent it with my Miguel email and I CC'd my Mila email. Should I send it with my Mila email?
I'm pretty sure I saw it, because
Oh,
I saw an email from someone who I think it's you, like in the middle of the class.
Yeah.
I don't think it was anyone else. Copy link. 6160. Yeah, it's you?
Nope,
That looks
that's
like-
it.
No, okay. No, that one I've already responded to.
And look up my name, it's HOSCIN. Sorry.
Oh,
Yeah, that one.
okay.
Wait a minute, you just pull up. No, that's not me again.
Okay.
Very similar. I can show it to you.
HOS.
Yeah, this one. Auditing student access to materials and definitely. So if you're just looking for Hussein, HOSCIN. No. 61. Okay, with the IFTJ.
Okay,
That's it. Thank you.
no problem. Yeah, and you can do the same if you can email me and then put IFT 6163 just like in the header, so I know that's for the class.
Yes. I can reply for this. This is the first email.
Sure. Yeah, if you reply to that, I'll send you an updated.
Okay.
schedule.
That's right. Discord.
Sure. Yeah, no problem.
That's going to be here.
Yeah, it'll be either in this room most of the time and once and twice over in the other Agora room, which is across the hall.
So
Yeah, on Fridays it's here and then on Wednesdays it's at UDM.
yeah, which, good.
The Claire McNichol building, Z210, I think. But if you email me, I'll share the information for the class
Yeah,
again.
what's up?
Okay, great. Uh, Mhm. All right, everybody. Everyone had a good break? Lots of stuff. Great. Um, okay, so we kind of covered one of those like main topics of thinking about the process for being able to train some forward dynamics model, make sure that it works well. All right, and now the rest of these slides are kind of like on the other side of this coin. Like, let's say that the agent is learning some forward dynamics model. How should it use this model? This might have seen at least like kind of like trivial from the algorithms that I've at least presented so far. But really, the number of different ways that a forward dynamics model can be used almost seems endless. We're only really going to have enough time to cover a couple of them over the next 2 lectures, but these are kind of like the most promising ways. So, and this is partly to deal with this problem too, is for the most part, sure, forward dynamics models can work really well, at least as a start. In practice, they don't work fantastically. And by work here, the tricky part is that a lot of model-free methods that we're going to talk about a lot more next, they basically function a lot better for when plans have to be longer into the future or things need to be robust. So model-based methods where there is some world model, there is some forward dynamics model, it's embedded in them in some way, because of maybe the errors that creep in, maybe because of having to learn the model, they don't typically get the same like asymptotic performance when training these models on a particular problem. So this is just this example where if something is trained entirely like model free or just model based. So this would be the model based line that would be carried across this graph. It struggles to be able to get like really good performance even after more and more training is performed. And that a lot of model-free methods where there's no model in there, it's basically just optimizing that reward objective completely. Those end up getting like much higher performance for most of the times. So, and this is a little bit about, okay, why is this happening? You think that, okay, a model is good, it might seemingly make things pretty sample efficient, but in the way that it's being used occasionally, it doesn't always provide the right kind of structure, the right kind of thing that doesn't hold back any other like corner of the algorithm that can suffer from some other challenges. For example, like if the model is being used to plan forward into the future and like one state at a time, all right, accumulation of error is going to be a problem for the agent. It's going to creep in really quick. So it's not going to be able to plan very far, potentially, and at least keep accurate models and being able to work well. There's also some other, I'll call them more mundane reasons, but they're definitely things to consider. One of the weird ones is actually, okay, if the model is being trained and if the model is just using something like mean squared error for being able to predict the next state, and then it's using this to be able to make predictions, in some ways, not all state features are equally as important when it comes to the planning problem, not just the prediction problem. So you can think of this robot here on the right. If this robot was trying to learn how to walk and it wanted, the model that we want here is something that understands the dynamics for walking pretty well. Some data can be collected on this for it moving around and hopefully doing some walking. But then the model is going to distribute error across predicting all of the different joints equally. And this isn't going to be great because, like, if I give you 2 examples of walking, and like another example of walking, did any of you see the difference in the walking that I did? I only moved my finger a little bit, but that thing has as much equal weight in the loss function as the hip in this. So if this thing needs to learn how to walk and predict for it really well, it really shouldn't care about how the fingers move. I mean, even in this case, we, in this work, didn't even bother to put fingers on there because obviously they would just be a distraction, even in the loss, and make things even more messy. But this type of stuff ends up becoming more and more important, especially when we're talking about real problems and there's capacity limitations on the model. And, for the agent to perform the best, it really needs to predict stuff most important related to the task it's going to perform here. So in this case, I can give this nice example for walking, and there's a lot of other cases like this as well. And there's going to be a lot of mundane as well cases we'll talk about in a bit. Or even if you're training something like a 4 dynamics model that's using vision, okay, does it really need to predict the background as much? According to the loss function, the background is going to be just as important as like, if it's like a surgery robot that's trying to figure out how to cut things and be careful. Okay, if it happens to see the stuff on the floor, that's also going to be included in how the model's being trained. And it shouldn't really care about any of that stuff. At least I would bet most of us would ignore most of those things. Yes.
Learning books also apply this that idea to the planning model as well. Like, you know, if I'm trying to use the planning model, it's like, okay, I think my head is an action. I also don't care about with the background, things like that.
I mean, yes. So there's a lot of work that tries to target this. If you're going to look up something, what you should look up is something called decision-aware planning or decision-aware control. What it's really going to do is try to figure out how much those decisions for each of these different predictions are going to end up being weighted according to whether or not that model is going to give like high reward in the end for the agent. So if it's not like correlated with something about the reward, maybe this particular state factor is like useless. Not useless, but at least unimportant for the task. Otherwise, there's a lot, that's at least like a community in a particular area, but there's definitely papers that'll figure out, I don't know, different ways to get around this. Often it'll kind of go a different way where, I mean, the people that are engineering robotics and trying to make some of these models, they'll just basically leave out some of this information. They know it's unimportant at that time, so it's a bit more engineered, but you would want to learn this more and more at some point, especially, well, if we were to make more like new or weird looking robots, it's not so easy to tell what should be left in and what should be left out. Yeah, okay. Other questions? All right. All right, so then now starts kind of the dive for, all right, so now how can we use either language models or some other models that we'll talk about to be able to help with some of these problems? And in this case, the problem is to figure out a plan for the robot to actually execute. All right, we'll start with LLMs here. And from there, there's really like two options that LLMs could be used. So basically the LLM could be treated as basically a black box. It's this fantastic world model, and it can be queried for solutions to planning problems. So basically the LLM is the actual forward model. Maybe there's something, well, this is the part where it gets a bit murky, but we'll get into at least a couple of examples for this. But the somewhat challenging part, or really the part that's being put on whoever's designing this algorithm, is being able to specify kind of like the planning schematic in some way well. You know, if we typed up on an LLM, okay, how can I go about making coffee? All right, that's maybe helpful, and it might give you a bunch of stuff. It might even just say like open up Amazon or Starbucks or something like that and order coffee. It might also try to give you a more detailed plan about like going to different locations. But then that depends on whether or not like your robot can process that plan. The robot does not speak a language. I mean, it technically kind of speaks a context-free grammar for all of like the computing nerds in here, but this is not a spoken language in some way. So at some point, there needs to be some translation. These fantastic natural language LLMs, the robot still mostly just speaks like well-structured code. And there's even some like really specific ways this can be done because there's been things called like planning grammars for a while. So it's possible to then like specify the entire planning problem in that planning grammar and then ask the LLM, okay, now produce a plan given all this structure according to this grammar. And that's usually easier to execute on the robot, or at least people have used these grammars already on tops of robots to be able to get to control them. So that means if the LLM can operate inside this grammar, it can just like directly start to interface with some of the libraries that have been developed already. Maybe that's good, but there are also some serious limitations to some of these grammars. So they don't always specify things well. And it might even have like something in the grammar that says, okay, like determine if the cup is half empty or full. Okay, That's actually a really complicated like perception problem. It's not just, it's great, it says this in text, but sometimes some of these things that are spit at like come out of the language model, really, really difficult to actually like even design a system to do that. So it's like optimistic in the plan as well, not just because it might have some errors, but it might be kind of forcing a lot of development to be put onto some system that's now making the controller to understand this plan. And sometimes making that system is like even more effort than like coming up with a plan and training an LLM. But that's a different discussion. Well, we'll have a bit of that discussion today. The other way to be able to do this is, okay, instead, very much like what we've talked about, like in the class, like basically use the LLM as a forward dynamics model, give it a state, give it an action, ask what the next state is. Sample the LLM, you know, T exponential times in order to find a plan that can work well. And this is a possible way of doing it. In fact, some people, even some robotics people are going this direction too, because there should be some kind of dynamics model inside of the LM. It's just occasionally difficult to get to. And it seems that so far, actually, the version on the bottom is at least more tricky to get working so far. Most of the papers, certainly some of them that have been like put out for the reading list for the class, are more in the group here on the top. Like express the planning problem, ask for a plan. Don't use the like LLM directly as a forward dynamics model. Okay. Does that make sense? Any questions so far? Okay, because these are both a bit, they're both a bit weird, but we'll go into some examples. So then like kind of trying to formulate this as something that makes sense, considering that like LLMs are kind of a soup of a whole bunch of different stuff. So trying to give a little bit of a formalism. So this is basically, you know, one way of thinking this is now just, you know, ask basically the LLM for some plan, maybe execute one action. That's very similar to this bottom one. So we'll try to express this in some changes to algorithms, although the papers tend to change, like alter a lot of different things about the way they're structured. Okay, so basically one of the problems are, and I don't know, has everyone heard of prompt engineering before? So this is, it's kind of a prompt engineering problem, whatever prompt engineering basically means. But basically, the problem really is there's some function, which is now our pre-trained LLM. All right, I'll draw it up here. Some function, and we want to give it some prompt, and it's got some parameters already and maybe some current state. But there's different ways this prompt, like this input, could be formulated inside of this function to give you a better answer. And to be honest, this isn't something that's really been specific to language models very much. People have, you know, different parts of research have pre-trained some sort of model or had some sort of function, and they figure out how useful it is to do other things. So it's not entirely new, you know, just for language modeling. Okay, so let's look at some of the options here. There's the start for this option in this kind of neat paper that was being able to construct some sort of prompt. So there's here in this example, okay, there's some task, shave for whatever reason, the robot needs to shave. I haven't quite figured that part out yet. But anyway, you know, obviously it asks it some steps, and then the LLM will then produce this, okay, step 1, grab a razor, step 2, switch on razor, I guess it's electric, step 3, you know, put razor to face. Sounds terrifying if you're a robot. And then, you know, provide some of this to the pre-trained causal LLM, and then, I don't know, new step for the next step and how this is actually being computed for any of these different steps. And then basically it's this prompting process. Okay. Did anyone read this paper, I think, as part of the reading list? No, I don't think this was one of them. Okay. So any thoughts about this prompt so far? Does this seem like this is going to start to be easy to use? For example, I want to kind of pick on this one, so this covers everything too. Okay, what does put razor on face mean? And when I think about it a bit too, is like, if we're getting into the ugliness of this, because it is kind of hilarious, but at some point it is, now the LLM is going to spit out this like kind of command, think about how to translate this into something the robot's going to do. Let's pretend the robot has a face and needs to shave or something like that. It's not a fantastic example in the paper. I mean, what does even put on face mean? Does the robot have a face? Most of the robots I have in my lab do not have faces, so I don't really know where this would go. Yeah, but then, all right, so now what are actions the robot can actually do? Yeah, I mean, even this. True, but that part also gets tricky because like an LLM hasn't really been trained on robotics data as much. So if you start to ask an LLM to like rotate by some amount and do something for some robot that maybe didn't appear, which is great because these days LLMs have been trained mostly on data from 2 years ago, and the amount of new robots that have come out in the last 2 years is kind of staggering. So it's actually going to be even harder to get this working. But there's like many problems, definitely one of them. Yeah, did comment? Yeah.
You represent that there is a core space under the structure, the structure that is all base and it has certain coordinates, no lengths and edges. And then for the other one, it's okay, and then the base, and there's a set that says, okay, this is space versus base on core.
Mhm. Yeah, I mean, that can help. I think I'll mention it here. So, but that also assumes, yeah, like some structure for the face. All the robot faces, I suppose, would be the same in that case, or at least hoped down to some design factor. But I think part of the challenge with this too is, all right, well, who's doing that? Like, who is constructing this thing, and who is making this algorithm that understands the face and the geometry? I at least want to say, all right, I want to pull out my lazy hat again and be like, okay, are we writing this algorithm? This sounds pretty hard. Seems like the LLM is doing the easy part right now, and the hard part is getting put razor on face working with like confidence. And by confidence, I mean like determinism and have it working well. And that becomes also more tricky. Questions? No. So this is now, there's sort of this a bit of challenge where sort of they're switching on some of this other stuff. But if we're going to start using these models, we don't want them, well, we certainly want them to solve like the entire problem, not sort of like maybe they solve part of the overall planning problem a little bit better, but actually now there's a couple of symbols being used and it's still having a hard time like specifying the rest of the detailed part of the problem. This has even been like a small limitation for like LLMs and transformers. They're not always fantastic at handling the high frequency, low level control stuff, like even partly by design. And that might mean, okay, maybe at that level of control, we are not going to be using LLMs and transformers. Potentially. Depends. Maybe we can probably work out some of the other engineering challenges, but an LLM at least hasn't been the right way to go so far for like controlling like joint level stuff to certain degrees at certain frequencies. It just wasn't in like the thought process when making LLMs, and it's a bit far outside of their design plan. Yeah.
Would it make sense to take price to delegate like step 3 to some more well understood program that doesn't have this black box dynamics? Like you wouldn't, I wouldn't want a black box bringing a razor to my face, right? I want like, use Cplex and make like a polygon take a face and program and bring it to maybe LLM delegate that program.
Sure. I think that's part of the idea. And at least from what is also done in this paper and some papers that are coming up with processes like these, I just want to make sure we don't miss the point that like the harder problem might be that program that does this, at least at the moment, the coming up the LLM, because in many ways there's been what I'll call like classical planning algorithms that might have been able to give a solution like this 20 years ago. And certainly though that the like the art and what would be really nice to get working for a robot is like one system that does all of this. And we do kind of like possibly a nice way to do this is like learning this all end to end, but also down to the details. Because then there's also the weird part where like, okay, we've maybe handled put razor on face. And now, okay, do we need a whole another one of these control libraries for like put razor to arm or something like that? And it'd be kind of related to how we talked about generalization and reuse. You know, if we're building things, what I'll call the old fashioned way, it's hard to, you know, design into this algorithm for it to figure out how to do the reuse and what can be extracted from that. So true, yes, but there will be advantages in trying to like push more of the structure into the models that we're learning as well. Because hopefully they can handle some more of these pieces. Because the put razor to face is like one example for like a million different combinations of things. And it's not going to be much fun to make a million combinations of these very specific designs. Hopefully these can be like data motivated somewhere else. And we'll get into that more throughout the class. I mean, we kind of got into it a bit in the behavior cloning part. So we could, you know, potentially have some models behavior cloned, take some goal. But now these don't always communicate with each other. I mean, so they can communicate with each other, but they're not trained together yet anyway. So it might mean, look at the behavior cloned goal condition policy is going to have a bunch of things that the LLM is going to spit out, and it's going to never be trained on any of those tasks. Like it hasn't seen any of them yet. We can hope for generalization, but there we should probably be a bit careful about that hope. So we probably instead, we could just train all the stuff in like a connected way to cover the data space pretty well. Likely a better chance, or at least seems like a more fruitful recipe. Unless anyone is totally against that recipe. There's at least some like variation in ideas here. Okay. So yes, so this is, like I was saying, this is a pretty, I'll call it like flexible natural description of what the plan would be. Different things to do is to use PDDL, which I think is like planning dynamics description language. That's one of those words is probably incorrect. But this is where instead of this, like the planning language describes beforehand what actions are actually available that like the low level control can perform. And then now if this process is given to the language model, it should only generate actions that might actually exist like in that operational grammar. It's kind of like providing an API for planning, and then at least it has those options. So it can't specify, well, shouldn't, but who knows, the LLM is not perfect, but it shouldn't provide, or in the plan that it generates, there shouldn't be actions that aren't in this grammar from this list. And there's also some extra constraints and things that can be put in there, and like a utility function, things like that. So it's pretty well designed. All right, but then the other avenue that we should talk about for a bit is it's also possible to now make a more literal API. And I don't know how many of you have read into this a bit as well, but you know, like ChatGPT came out, it was possible to like make plugins that were built on top of ChatGPT. So you could make a plugin to control your robot at home if that's something you felt safe enough doing. But then this at least provides, at least like in a programming computer science space, this API is made. Most likely someone who's designing this robot now has some understanding of the actions the robot can take. And then from that, the LLM can then be at least used to like now figure out the plan. And there'll be sort of like some processing step in here that might like filter that plan a bit, maybe do like some synonym matching on stuff that might actually exist in the plan. And it's the same as this other action that was specified, but then eventually be able to control the robot in that way. So this does provide more structure. It does get a little bit more now towards that step of, well, now I don't know, what's left over in the challenge here is being put on like some other programmer that's trying to figure out how to map the outputs from LLMs to actual actions the like robot can control. And that's hard. We'll get into it for a fair bit, but that's why there are so many people working on like goal-based control from vision, is because making that low-level controller is actually pretty challenging. Partly for a number of reasons, but kind of just like the ugliness of the dynamics of the world. And it's really hard to be so robust. Okay, does that make sense? Any questions about these? All right. Sure. I don't know. Possible class project there if you feel really optimistic, but you'll also, like I said, run into these challenges of dealing with that interface is going to be like the hardest part of that project. And that's what I mean here. There's still a lot of limitations to these models. It's still pretty hard to be able to make this interface and have it work well. It's sort of, maybe one way to think of this is like, okay, we've had like Google Maps for, wow, maybe 20 years now. We still don't have self-driving cars very well. There's maybe a few. It was like, seems like Google Maps was easier to make than getting the self-driving car to work. And like, why was that harder? The thing that actually interacts like tires on the pavement on the road. And that took much more time and engineering. So there's something about that. I don't know if people are familiar, this might be related to Morvig's paradox. Like just some of the easy stuff is actually really hard for robotics to do, which is just like grabbing things and moving them around. But planning might actually be easier. And people aren't actually great at planning. But that's a different problem we can get into if there does happen to be like a human robot collaboration part to this class. Okay. Basically, so what this kind of boils down to in terms of that algorithm that we've been talking about so far is all these steps stay the same. Okay, execute this action from the LLM. Okay, it's just, this is not as simple as it may sound. If it is, put something on the face. Maybe the robot has a face, maybe it's a dog, it doesn't even have fingers, who knows? So it might not be a very simple action to achieve. And there's kind of like two options here. Either hire basically a team of robotics engineers to figure out how to solve this, or maybe start to develop a different like machine learning system that can handle all these goals and work well. Okay, so then let's think about that process now. So if we're going to have potentially this LLM that's specifying plans, it's really like, okay, what tools are available to us to help make a system kind of quickly that'll then be able to realize those actions better. So there could be here, this is sort of like one example that at least takes this one step to give us like a proof of concept here. So maybe an LLM is used to be able to specify the plan, and then something needs to be constructed to actually be able to satisfy those actions. So then one thing that can come along and basically be used is clip can be possibly used here, because one of these questions might be put item on face, but if we go back one more step, it's like grab razor. What is a razor? I mean, they kind of maybe change each year, but so like before we even get to the action, there's a perception problem. Essentially now, performing a perception is now actually an action that it needs to figure out how to do. So then at least is there some system that can perform this perception part, and maybe even like ask the LLM to grab this code and be able to put this together. So now it can at least satisfy a few of the steps in this plan. So in this case, fortunately, there are a couple of other models. So it's possible to grab like the clip like set up there. It still has this text-based query for what it's looking for inside of the model. Give the current perception that the robot is looking at right now, like this overhead image or this egocentric image, and now can at least like attempt this actual action. And it's just this perceived part. So like, is this a razor in this actual image in combination with this clip model? And then from that, I can at least, if we're doing like event-based planning or something like that, it'll either say, okay, cool, let's manage to like get past this step in the plan, or it will not have found a razor. It needs to keep looking. So now there's kind of like this subroutine for finding a razor here. And at least it could generate, okay, this perception model can be used. Now the agent needs to wander around randomly in the environment, taking pictures, hopefully until it eventually finds a razor, or in practice, times out and gives up and sends a message on Slack to whoever student is supposed to be looking after the robot right now and goes and helps the robot. But basically the solution here is always a human comes and helps the robot whenever the robot doesn't work well enough. Okay. But even in this process, so the LLM can generate some code, but like you're thinking even more, before we even get to actions, like where does this start to get tricky in here? So any ideas? This is kind of like think more about the steps here that would come out of the LLM model for grab razor, switch on razor, I don't know, something like that. Where do these also start to get tricky? Yes. Yes. Can you say a bit more about that? Like, what's the context here? For example. Mm-hmm. Yeah, that's basically it. There's always, so this is also, if we're thinking about like that self-driving car example where like the wheels have to actually touch the environment and things change. This kind of now gets into like with a robotics context and everything gets in there. It's like now to achieve all of these things, who knows what other kind of like software perception control systems are needed to satisfy these particular steps. And they show up so much faster than you might expect. I mean, like, it's not even that the agent can get like 10 steps through one of these plans. Usually the very first step is a robotics problem on its own, basically to figure out, like, just like figuring out where the razor is in the process there, because it's existing in some sort of environment, basically means almost every time. One way to maybe think about this is instead, yeah, that being step one is grab a razor. What would be a nicer thing to come out of the LM is like step one, grab a razor / here's the program for figuring out how to grab a razor. And it's going to be like probably contain half of the stuff from your like average probabilistic robotics textbook to figure out how to do those things. But that's like what's needed for each one of these steps. Each one of these steps is its own robotics program, basically to figure out how to solve them. But that's part of what might be kind of a really actually good thing. And what some people have explored here is then actually like using LMs to generate code. And here, like specifically, like expanding on these, and now instead of the policy output for the LLM being like joint controls at certain angles, it's instead, all right, give the code for that actual description for how to design this policy, like the Python code that can be run on the robot. There's going to potentially be some limitations to this as well. But this is maybe one way of like trying to expand this grab a razor into some concept that at least maybe an LLM has a chance at being able to give an okay solution. There's going to be some challenges here as well, because in here, you know, I would suspect like if it's doing a good job, one of these outputs is going to be, all right, grab a clip model, use it as a perception system, and maybe this will work well and predict. But it's really hard. You know, basically to have these LLM models be able to predict in like design algorithms that get more and more sophisticated. Like if it needs to do perception, should the LLM literally kind of like produce out, here's a convolutional neural network model and all of the weights for this model such that it'll be good at perceiving razors? Is that really what's being described? I mean, it is sort of what's being asked of it, but is that really the intention? Like that what'll work well here? And this gets pretty tricky. It can be fun though at some point, and I think there's definitely a lot of people really interested in this direction, because if some of these hurdles can be overcome, then maybe this is a really good solution, because in the end, it really is a program like running on the robot, you know, in some way. But I don't know, I'm not quite sure if there's like enough training data to meet the fidelity that people might want from this so far. Like to be able to spit out a program basically for any one of these steps that might come out of an LLM. I'm sure we can probably start to imagine some pretty weird steps that might come out of some of these. And maybe there's an algorithm for that, maybe not. So the training process here might still be kind of tricky. Okay, does that make sense? Yeah, any questions about that? It's kind of it's a weird concept, but it's actually kind of a nice concept. But it, at least at the moment, is a bit trickier when in one of the lines of this algorithm still has to be, you know, like perceive razor. It has to expand this into like an entire machine learning paper, potentially, and like all the code that went along with it. All right. No questions? It's also potentially a fun project idea. We'll see. There's a couple of actually, this is one of like 3 or 4 papers that have been done in this area already, and it can actually work pretty well. As long as always, is the kind of trick in some of the research papers, as long as the task that's being tackled in the paper isn't more complex than it absolutely has to be able to show that this method might work. So here, you know, always in some of these papers and pieces of work, the tasks that are tackled in the work are kind of carefully chosen. Okay. There's also this part. So there's kind of so now this is a little bit more onto the second suggestion, or if there's some large trained model, we can even kind of get away from LLMs at this moment. But we can think about LLMs for now, and it's sort of related to this, like how well do they understand dynamics? So now the second option in here is treat the language model as basically just a forward dynamics model. It can specify the state, the action, and it can output the next state in text, and then be able to provide that information. But often this comes up a lot in the community because it's great that the LLMs have been trained over a lot of information and specifically a lot of text from the internet. But maybe I'll ask this one kind of proof of concept question. You know, how easy is it to describe the physical world in text? I'll give a good example. Let's say I'll give you 3 sentences and you can all describe to me how exactly that ice thing fell outside of the class. There's some block of ice. It's really hard to describe all the dynamics and details that are going on with that particular thing. But that is what the robot will eventually need to know the details at that level to interact in this physical world. There may be some of this on the internet, and I really applaud those people that went into that kind of incredible detail to describe something, potentially down to that fine amount. But it's basically there's still going to be some difference between these two. And the community tends to call this part of the grounding problem, where like there's a lot of knowledge inside of the LLM. It doesn't necessarily have knowledge about like the grounding of how the physical world really works, and that it has a hard time being able to connect these together. Like an LLM, an orange is like a symbol, but like if everyone has like eaten an orange in here, it's like it has a taste and like a meaningful color that's determined by physics. And sometimes those things are important when it comes down to planning. If the robot is supposed to go grab an orange and there's a bunch of old rotten oranges and a bunch of new ones, it doesn't maybe not necessarily know the difference between these two and why it would stop in its plan and throw out the old ones and then grab the new one and go head back to bring that to whoever asked for the orange. Something like that. Okay. Yeah, so there's at least this concept where it's okay. It seems like these models don't have grounding. The tricky part though is the community still doesn't have a great definition for what is meant by grounding. Like, what is this model missing? I suppose this could even be asked of ourselves too. Like, how do we know that an orange is an orange? And how do we know its dynamics well? Something like that. So there's still a lot of discussion in the community. I'm not going to focus on this too much because I prefer to focus on things that we have more details about that we can explain. But just keep in mind when people are talking about lack of grounding, it's kind of this like physical understanding or dynamics of how to use the objects. Yeah, one way though to basically start to be able to overcome this. So one, which is basically remember our like duct tape solution for basically every problem, collect some data on the actual system on policy. That's, you can't get much more grounded than that. And then this will provide like some link towards the old data that was in the current model, and the new data that's coming in should likely be able to perform better. Oh yeah, and there's a variation on this too. Basically, if you've got this problem where we're going to ask the LLM for a plan and it produces a plan, now ask the LLM again if this plan has good high value under what it understands about the dynamics. And then ask a second question to like some model that's actually been trained on the dynamics of the world and see if this plan still has high probability. So it's kind of like filtering these plans by some other model that's much more grounded. Doesn't have to be an LLM, but something. And then at least it seems like it's possible in the world. So these two options seem to be like two of probably some more directions to try. Okay, so then there's basically the next step after this. LMs are great. What about video? And there's a lot of motivation these days. Okay, if LLMs are missing the grounding, and if what we care about is this grounding, and the agents just can't operate without it, maybe video is a much better source to be able to get this data, or at least like these representations, this understanding. And the nice part is there's certainly a lot of models that are being created these days, but video models kind of come in a few different flavors. There's usually some input. It could be some text, something like that. Often it's also something like an image, can even be another option. And then from this, there's going to be some representation here. And this is kind of what this whole process is about, is this video text input model should learn some sort of latent representation that kind of describes what should be generated. And then some other video generation model that then like takes in this input, generates a beautiful looking video. And then there's a lot of good representation inside of this particular encoding and potentially a really nice looking video that comes out of it as well. And because of this process of basically having to go from, it's like now, if I describe to you the word orange, but instead I said like juggle an orange or something like that, if you can like generate this actual object and understand like its process, if it was rotated, how it would look on the back side of the orange, if you drop something on top of it, how the dynamics of it are going to form. So as we go through this process and try to like add more and more details to this text to make a more and more complex scene, and if this model is still generating active, correct videos for all these different dynamics, it likely has a pretty good understanding of how the dynamics actually work, like that grounding that's going on in the world. And that's at least where I'll note this, Feynman's kind of common quote, what I cannot create, I do not understand. So if your generative model, though in this case, can create all this stuff, it may have a very good understanding about what's going on. Okay, but now's where we can have a little bit of fun to go through this. So there's a couple of great examples. As I was going back through the history, there was even a video GPT model back in 2021, which I guess is like eons ago, according to the, machine learning race that happens these days. But this was basically just this design, like much at a smaller level. So these are like 64 by 64 images, making up videos, learn some type of code book from a bunch of encoded videos and outcoded videos. And then from this, you can kind of like randomly sample stuff into this code book and start to generate pretty nice looking videos so far, at least at the time, that would look quite nice. So you can look at a few of the examples here. Yeah, this should still work. So it's nice. They've got, of course, some of these papers are chosen because they have some great robotics examples, but these are videos, like totally generated inside of this actual model, not really things that go as particular input into this. And I know they're not super high quality yet, but this was still 4 years ago. Like I think even, no, I guess H100s came out around that time, but they weren't in giant piles everywhere for people to train things. And you can, a lot of other examples for a couple of different unconditional videos. Some might say that actually part of the challenge in being able to explore this video condition research, kind of the lack of videos that were available. YouTube is okay, but it's not always totally accessible. But creating nice data sets of diverse videos is something that takes time and enormous amounts of disk space. So this is almost a bit of a data science problem on its own. Okay, does that make sense so far for like these video generation models? Okay, and then the challenging part and where we're hopefully getting to with some of these is being able to get them to generalize pretty well. So now, like in one of the papers that came a little bit after this, is being able to do some image condition models. So now you can provide some image and then maybe some text, and the video generation model can edit this video basically here. So I'll give some examples that they've got on this page. You're welcome to go and read some of these papers for like the details of the architecture. But here I mostly want to get to some of the examples so we can think about how to use them. So there's like one input image that's given here on the left, and then some additional text for, I guess, being angry or disgusted or neutral. or surprised, etc. Or for some particular given image, being able to wave, to clap, all those sorts of things. Okay, so then given these examples, can some people start to imagine what you might use this for robotics problems? Thoughts? Yeah, like even here, we already mentioned that like it's part of the cost problem for being able to generate data for robotics. So like what if you've got this, and then you can start to at least generate video data for your robot system to start to fill, hopefully, your data set with sort of accurate things. So at least you can start to train your model. So that's one option. Obviously, there's really a whole bag of different things you can do with these as well. Any other ideas? Yeah. Mm-hmm. And this is kind of related to like the IDM stuff we talked about from before. So you can either maybe fill a data set or like generate the solution, but it's only the video. The robot still needs the actions. So it's possible like train an inverse dynamics model, then produce the actions for that. So if you've got a good inverse dynamics model and a good video generation model, it's possible to be able to make pretty good control policies from this. There's still like work in this area, but a lot of what some of these projects are doing both of those. There's even, I don't know, there's also different ways to like add some variation to this, even for the data that's being looked at. So like, I'll just mention like one of the good reasons, kind of in addition to generate data, but like what if you want to be able to make your model more robust? So you could have, let's say in the video, this is mostly in the background, and in the foreground, the robot is like assembling some object. So this could be used to add more and more structured variation to like the background of the image while the robot is training. And then it should learn to ignore that stuff because it's not actually important. And this is much better and structured because the other option is to add like Gaussian noise into the background, which is not something we really see in the real world. So we would want to be able to do this generation process and basically add this noise such that it's more of like a real world noise of how things will change. Learn to ignore that. Okay. But yeah, this is definitely a growing area of interest, especially in robotics. But I guess video generation models are now starting to become kind of good and reusable for the most part. Let's see if we get to it. Maybe I'll give like one asterisk on this as well. It's just part of it. You know, sometimes the amount of pixels matter. So like in this case, you've got this human that was waving. That's fine. But what if part of the problem is now you've got a humanoid robot and the agent and robot needs to understand how to grasp objects. So there's maybe not enough pixels inside of this particular image to understand how the fingers are moving on the robot. So this is where like maybe scaling up in terms of model size, but more importantly, being able to handle more high definition video means that like, well, now what's going to be embedded in what is going to be this internal model is going to get better and better because now it has to understand the dynamics, even at a fine scale for how things interact. And this might have been like a lot of the problem for like doing the self-driving car problem is understanding the dynamics at that level and that frequency and that difference. So this is still a little bit related to the concept from before where like we want the agent and this model to still be good, but it still needs to be good for planning. So we haven't really answered this question for some of these video generation models. Like, are they accurate in the areas where the robot is going to end up exploring and where the dynamics are important? Still a little bit of an outlier, and there still needs to be some more work there. But at least, yeah, there's a couple of fun aspects for, oh yeah. And so basically, how can these models be evaluated? Like this video generation model. It's occasionally a bit tricky because sure, it looks plausible, but very frequently, people are very forgiving in evaluating these models because they look great compared to like nothing. But to understand if they are like truly physically correct down to correctness enough for robotics, we might need some better ways to evaluate these. And at least one of these evaluations that I find pretty interesting is this one where someone took, I guess someone being these people, these authors here at the top of this paper, they take videos that were generated from Sora and then basically pull out the bag of methods from robotics, basically run SLAM on these, basically see was the geometry consistent inside of the videos that were generated, or is it making up stuff inside of the actual videos? So they did analysis across a couple of different models, but there's some really nice like videos and pictures here at the bottom where, okay, from what I remember, the green is actually good. So if this is the beginning of the video and this is later in the video, it's marking correspondence and geometry across these two videos. Such that now as like the camera moves around and the things move inside of the scene across each image, the geometry and dynamics is still correct. So it's fun and actually a nice way to do this, to basically unpack our robotics toolkit, which we normally use for sensing the environment, and using this now on these generated videos. And that is a nice way to potentially be able to evaluate some of these. You can see, I guess these are a little small, but if these are like short video clips that are produced from some of these different models, and I think this one is from Sora. I think there's some audio in this as well. But I remembered there being a really nice correspondence video in here somewhere. Oh well, this is definitely one way to go about evaluating these at scale, and hopefully in a slightly less biased way than having us all just look at them manually. Slam in the video. So here it does help for the video to be a little bit longer, but you basically treat it the same way that some like video-based SLAM model would work. So it's going to compute a lot of stuff inside the scene, start to make like marker points inside of the scene, and then see as like the robot moves. It's basically like inverse Kalman filtering here to see whether or not things correct. Basically, it's like running a Kalman filter over this video and say like, okay, was there some structure in this, or is the Kalman filter really confused for what's going on? There's a little bit more to that, and I don't remember exactly the details for which algorithms they use. But here it looks like they're using stereo matching results across these two images. That's one way just to see what works there. I bet you could probably go even deeper into this and pull out some like more complicated SLAM algorithms that exist these days and use that to evaluate these models and see how good their structure is. Yeah, and then hopefully, maybe this can be used as a nice loss to like improve the embedding that's inside of the video generation model. Here we don't know because this is Sora, which we don't actually have access to, but there are at least, as of today, there's a few video generation models that are possible to use. They require pretty large amount of compute, even to do some inference, but they're a start. And maybe this is actually a slightly better direction than going the LLM method, at least for robotics stuff, where having to move stuff in the world and understand those dynamics matters a bit more. Okay, other questions? No? All right, cool. Great, that's it for today. I think we'll come back to this a teeny bit, but besides that, have a great weekend.